In this video, we're continuing to work on some general solutions for linear differential equations. Our next example, we want to obtain the general solution to the equation y times dx dy plus 6x equals 7y to the fifth. One extremely important thing to notice right away is the way that that differential is stacked. It says dx over dy. That means that in this problem, x is the dependent variable and y is the independent variable. So if you look back at what we said our general form for this equation should be, our x's and our y's are going to be flip-flopped. So our general form is going to look like this, and this is what we're going to want to match. Dx dy plus p of y times x equals q of y. And all I did is flip-flopped all of the x's and y's in the very first general format we said we always want to start with. Well, ours is not in that format. We also have this y value in the first term. And in order for us to be in the form that allows us to start solving, we want that derivative all by itself in the first term. So to get rid of the y, we're going to have to divide every single term by y. And when we do that, we get dx over dy. Now remember, the p of y is multiplied by a single x. So what I'm going to do, instead of writing 6x over y, I'm going to separate the 6 over y times the x, so it looks more like my p of y times an x. And that is equal to, we can simplify on the right, we just get 7y to the fourth. So this right here is our p of y, and this is what we want to use to figure out our mu, which is our integration factor. Remember, mu is e to the integral of that p function, which here happens to be a function of y. So mu will be the integral 6 over y as our exponent of e. That antiderivative is equal to 6 natural log of y. And remember, we're not allowed to cancel the e and the ln until we move that coefficient. That 6 is technically in the way of allowing us to cancel, so we have to use one of our properties of logarithms that says coefficients can go back up as exponents. So we've got e to the natural log of y to the sixth, and now they cancel. So our mu is y to the sixth. So if we multiply through this equation by y to the sixth, and I'm going to simplify along the way, we get y to the sixth, the dx dy, plus 6y to the fifth times x equals 7y to the 10th. The left-hand side of our equation here matches up perfectly with a product rule. The left-hand side of our equation is just the expansion of the product rule when we're asked to differentiate with respect to y. Our mu function, which is y to the sixth, times our dependent variable, in this case is x, equals 7y to the 10th. Because x is our dependent variable, our goal here is to solve for x. So now we've got just a couple of opposite operations to perform. We can get rid of the d dy if we integrate both sides. That will leave us with y to the sixth x equals 7/11 y to the 11th plus c. And then we'll divide everything by y to the sixth so that we can isolate our x. And I like to divide every single term individually because every term is going to simplify differently. So what I'm left with is x equals 7/11 y to the fifth plus cy to the negative 6. This is the general solution, since we have our arbitrary constant there, for that linear differential equation. We're also going to look at solving a couple of initial value problems, which also means we're going to be finding particular solutions. This still involves us going all the way through finding the general solution, like our last few examples. It just adds a couple steps onto the end for us to do. So we want to solve the initial value problem, dy over dx plus 9y minus 2e to the negative 8x equals 0. And y of 0 is equal to 3. dy dx, that means y is dependent, x is independent. We want all instances of y on the left, and any terms that don't have any y's move to the right. And then if the dy dx is by itself, we'll be in a format where we're ready to solve. So I need to add this 2e to the negative 8x over to the right-hand side of our equation to get this in standard form. Now that we are in standard form, it looks like our p of x is just equal to the constant 9. So when we solve for our mu, we're going to be doing e to the integral of 9 dx, which is e to the 9x. So when we multiply through the standard form of that equation there by e to the 9x, it should make the left-hand side of that differential equation match up perfectly with a product rule. And don't forget, the reason I'm writing this step out is so that we don't forget to multiply the right-hand side by e to the 9x as well. And then those will combine. The e to the negative 8x and 9x will make just a e to the 1x. So on the left-hand side, I've got the original first function, derivative of the second, times the derivative of the first function, original second. So this was original first, original second. We can collapse the left-hand side down into just a product rule, which is between e to the 9x times y. In order to solve for y, we now are going to integrate and then divide. On the left, the integral and the derivative just cancel. We get e to the 9xy is equal to 2e to the x plus c. The antiderivative for e to the x is just e to the x. And last step is to divide everything by e to the 9x. So our general solution is y equals 2e to the negative 8x plus ce to the negative 9x. We're not done though, because we were given an initial value here, a corresponding x and y value that if we were to go ahead and substitute them into our general solution, we could find what the value for our arbitrary constant is. So that is our next step. If we were just asked for the general solution, we would be done. Since we were asked for a particular solution, which is the same thing as solving initial value problem in this case, we just have a couple extra steps to perform. So now I'm going to mark where our extra steps begin. We've got y equals 2e to the negative 8x plus ce to the negative 9x, and we know that y of 0 is equal to 3. That means when x is 0, y is 3. So we're going to plug those in, and we're going to get, and y is equal to 3, so 3 is equal to 2 times 1 is just 2, and c times 1 is just c. To solve for c, we'll subtract 2 from both sides. C is just equal to 1. So if we plug that back in to our general solution, it will give us a particular solution. Y equals 2e to the negative 8x plus 1e to the negative 9x. And that the 1 is just a coefficient, so you really don't need to write it if you don't want to. Leaving the space in front of the e empty also indicates that it's a 1. So now we have a particular solution. We solved an initial value problem. There is no arbitrary constant. And that's the difference between our general solution and our particular solution. So let's look at one more initial value problem. We are being asked to solve the initial value problem, cosine of x times dy dx plus y times sine of x equals 8x times cosine squared x. And y at 2 pi over 3 has a value of negative 43 pi squared over 18. Now that value might look a little bit intimidating. Don't worry about it. All we're going to do is plug it in later, and hopefully a lot of it will simplify when we plug it in. What we need to focus on to start with is finding a general solution. So we want to start in our standard form so that we can identify our p of x, and the standard form has dy over dx all by itself in that first term. So we're going to have to divide everything by cosine x. And this gives us dy over dx plus, I like to write my x function first because that's like my p of x. Sine x divided by cosine x is tangent of x, times y. And then on the right-hand side, that cosine can cancel one of those away, and we get that it's equal to 8x cosine x. So from this format, we can see that our p of x is equal to tan x. So to find our integrating factor, mu, we've got to have e to the power of the integral of tan x, which is negative natural log cosine x. The e and the ln will cancel if we take this negative ghost one and move it back up to the exponent position. Once they're right next to each other, then they cancel. So the mu, all we've got left so far is just cosine x to the negative 1, which is 1 over cosine x. We are going to leave off the absolute values because our cosine is no longer inside of a log, so we don't need to follow the rule that it must stay positive. 1 over cosine x is the same as secant x. Mu is secant x. There we go. We're ready to go. Now, I'm going to skip a step here. I'm not going to show the entire process of multiplying through by secant x. What we're guaranteed is that the left-hand side will collapse down into the mu function times y inside of a derivative. On the left-hand side, remember, we technically do have to multiply through by secant x. So 8x cosine x times secant x. Well, cosine and secant are opposites and they cancel each other out. So this is just going to be 8x. Our goal here is to solve for y. Now we're going to integrate and then we're going to divide. So those guys will cancel. We get secant x times y equals 4x squared plus c. And to solve for y, we'll divide everything by secant x. And remember, if you do every single term individually, there will be less room for error. Secant in the denominator is equal to cosine in the numerator. So I've got y is equal to 4x squared cosine x plus c cosine x. This is our general solution. We were asked to solve an initial value problem, so we've got one more part to this problem. We're also told at the beginning this boundary value. When this value is 0, it's called an initial value because it's when x is starting off at 0. If it's not 0, it's called a boundary value. And that's not really important for you to remember, just a little technicality. So the y value at 2 pi over 3 is equal to negative 43 pi squared over 18. And what this means is when x is 2 pi over 3, y is equal to negative 43 pi squared over 18. We're going to plug those values into our general solution so that we can solve for the arbitrary constant c. So negative 43 pi squared over 18, that's our y value, is equal to 4 times x squared times cosine of x plus c times cosine of x. Cosine of 2 pi over 3, let's go ahead and get that out of the way right at the beginning. You could just type that in your calculator. Just be very careful. This angle is a radian. Because there's no degree symbol, it's automatically assumed to be a radian. So your calculator needs to be in radian mode in order to correctly calculate cosine of 2 pi over 3. When I type that into my calculator, I get that cosine of 2 pi over 3 has a value of negative 1/2. So I'm going to go ahead and replace those first. And I'm going to simplify as much as I can. I need to go ahead and square 2 pi over 3. So that's going to be 4 pi squared over 9. I'm going to get all of this multiplied together. It looks like I'm going to get negative 16 pi squared over 18 minus 1/2 c. And I'm going to add this value over to the left. And that's going to leave me with negative 27 pi squared over 18 equals negative 1/2 c. And then to solve for c, I need to multiply both sides by negative 2 because that will cancel off the negative 1/2. And I get a c value here of 54 pi squared over 18. And I'm pretty sure that will simplify a little bit. 54 over 18 is equal to 3. So this is just 3 pi squared. C is equal to 3 pi squared. Now, I am really excited that we got that because this did not start off looking like a really easy problem, but don't get too excited. That's not our final answer. Remember, we're looking for a particular solution, which is just a general solution with the c value replaced. So we need to write out the entire function y equals from right here and replace the c value, and that's the answer we're looking for. So y is equal to 4x squared cosine x and then it said plus c cosine x, but our c value is 3 pi squared, so plus 3 pi squared cosine x. And that is our particular solution.